Recording is running. We're going for matrices. So we learned a lot about vectors. Vectors are the easy stuff. It's just one row or one column of a matrix. A matrix is basically a vector that has a x and a y, so a two-dimensional vector with a lot of numbers, with m rows and n columns. For games, we typically focus on 4x4 or 3x3 matrices, so they are not high-dimensional, just 3 or 4-dimensional. So a common thing. Well, here's the mouse. Great. Matrices can be added. So adding two matrices just adds the components to it. You can do the scalar multiplication. Again, very easy. You just multiply the scalar with every component of the matrix. These are really the easy ones. And the hard ones are then the dot product of rows versus columns. And you have to have the same amount of rows in the first, so the number of rows in the first matrix has to be the number of columns in the second, because you multiply rows by columns. So here we have A and B, and A and B is multiplied by A with the first column vector here, so A times E plus B times G. And it also works with one row and two columns. Oh, no, you have to have, sorry, the other way around. You have to have the same number of columns in the first matrix and with the same number of rows in the second matrix. And then it changes, of course, the dimension. It gets smaller. And yeah, so that's the basic idea of matrix multiplication. So it's better to try it, actually. Really hard to explain it here without typing or having a blackboard. This is one atomic operation. I mean, it's not atomic, of course, but it's the atomic operation of most of we need in computer graphics. And funny enough, this is also an atomic operation for most of the AI stuff we're running right now. So yeah, that's also why NVIDIA builds these wonderful long-lasting electronic devices that power both games and AI. Matrix multiplication is not commutative, though it is associative and distributive over addition. So the formulas are below, just to keep in mind that you cannot switch A and B if you multiply them. A times B is not B times A. The rest works as we know it from elementary school. There is an identity matrix which is neutral on multiplication. So you have the identity which is neutral on multiplication. In real values it would be 1, for instance. Neutral over addition would be 0. And neutral over matrix multiplication is the identity matrix, which has in the main diagon, so where the component row and column number are the same, it has a 1, everything else is 0. So that's also nice, because if you have a matrix and then the matrix has to be a square matrix, of course, otherwise you won't be able to have an identity matrix multiplied with the identity matrix, then you always get this one out. And math is math. If you couldn't do the fun stuff, invent by the definition of the identity matrix inverse matrix, A to the power of -1, which actually creates an identity matrix when you multiply it with A. So that's the idea. So typically this matrix is unique, so there's only one solution to the problem, but it does not have to be a solution, so it's not necessarily there. Okay, something else we need, and that we actually need a lot, is transposing of matrices. So you transpose a matrix by just switching rows and columns. So here it's color-coded. That's the beauty of streaming it, that you can actually see the colors, or it's not on the beamer that you don't see the colors, it's on your monitor. That's the downside to it. Your own hardware is limiting you, not the university hardware. But on the other hand, typically your hardware is better than the university hardware. So it's switching the row vector to the column vector, and the same here. The green one goes into the center column vector, and the blue one, the last column vector. yeah, there are two major ways to represent columns, or actually vectors. One would be a row major, and the other one would be a column major. The numbers are the same, the possibilities are the same, but the ways to get there are different. So if you have a row major vector, then you have to multiply the vector with the matrix. If a column matrix system, then you have to multiply the matrix with the vector, so the other way around. Otherwise, it would not work. And that's basically it. That's all we need from vector math. And I'm just switching here to the other part. I just didn't want to rush it through the last time. So what we're actually shooting for today is coordinates and transformations. Yeah, unfortunately, it has nothing to do with the transformers. But it's still very, very necessary for actual computer graphics. Yeah, Sources, great book, gives you from 0 to hero version of it. It's a little bit older. It's based on C#. Yeah. On the other hand, C# is, while not being monogame anymore, it's the main thing in Unity. Okay, so we're going 3D. That's the whole idea. And what is the difference between 2D and 3D? There is an additional dimension, C. So X, Y, and C. And we have 3D objects. There are two 3D objects up there. No, up there. Here. Hard. The masking, the auto masking doesn't work. It looks weird, but it's still better than having none. Yeah, so the 3D objects are displayed on a 2D display, which is what we're doing right now, or on a 3D display. And the price question here is, why does it work with a 3D display? And that's actually not funny. At the final examination, one student actually mistook that you need for 3D, seeing 3D, you actually need more than a 2D display, which should be then two 2D displays, because then you can do stereoscopy. You can actually communicate the depth perception. Anyway, we'll not do that right now. We map it to the 2D display, and you can see two of them. Nice torus with quads. So you have squares that make up the big model, and then one that has been triangulated, and a few have been reduced. So triangles make up the torus. Yeah, now I have to get a new graphics card somewhere. Okay, so 3D objects are made out of polygons. Typically, they're triangles. So that's really convenient, because with triangles, not much can go wrong. Rip your wire. No. It's warranty. It's 4 months old. So it's a lot of emails. A lot of emails and yelling at salespeople, most likely. So yeah, I wouldn't afford the same graphics card right now. It's crazy. They're all crazy. But if you have followed the news, you might have heard that Intel is actually entering the market back again, and they have a valid option if you just want to do gaming and you're not playing Crimson Desert, which does not support Intel graphics cards at all. Then Intel has some wallet sensitive options there. That might be something. I was just listening in if that is my fan, because if the fan wears up, then that's the near dead end. As soon as I switch from Intel, they do this. Yes, I hope. Okay, so triangles are defined by 3 points, and that's pretty cool, because 3 points are always on a plane, on a single plane. That is where it cannot go wrong. Of course, many other things can go wrong with triangles, but all polygons, we can state that the more polygons, the smoother the object actually is. So what we're having first things first, for coordinate space, we need an origin, a frame of reference, and this is 0, 0, 0, and everything else is relative to 0, 0, 0. Oh, I just realized I should have started Blender before, because Blender was also configured to use the NVIDIA graphics card, and yeah, that's why my computer in the morning crashed when starting OBS. I will not open Blender to show it to you, sorry. We have to do that the next time. So for modern games, you typically have not only one coordinate space, but you have 3. No, actually 4. But the last one is different, projection space. And so all the positions have a relative, are relative to the center, and you have 4 coordinate spaces to travel from, and they all have different origins and scaling and so on and so on. And to put this all together, we need those transformations. So I actually have a lot of stuff running around here. So if we just have this very basic sketch, it creates a canvas, and the difference here is WEBGL. So we have a 3D canvas, and there is this simple thing box here. Okay, I'll just remove the rest. And then put it back in. Okay, so now we don't see the box. Why do we not see the box? Because we only see the front face of the box. We can make the box bigger, for instance, 180. Then, of course, it would be nice to have a background. Maybe make it a little bit gray, 200, so that we... Okay, on my left side monitor it looks blue. I thought, oh, why is gray today blue? But obviously it is. But on your end, it's gray, it seems like. And yeah, what we actually need is we need to see if it's a 3D thing. And for a 2D monitor, the good thing is if we can move it, then we can assume that it's 3D. Okay, so now with the movement, not stereoscopy, it's the relative movement of the whole thing that gives us, through the projection, a little bit of an idea. Okay, and what we can do, we can remove the one on the no-fill, and then we see a wireframe model. That is the whole idea. Okay, the orbit control basically is a cheap version of having the mouse orbiting the center. Wait, having the camera orbit the center with the mouse. Yeah, did I get it right? Awesome. And then, just checking, I'm still moving here. Great. Then we don't have to move the camera around. It's done automatically. And of course, we can set the stroke color, ever 128, and it's grayish. Yeah. Okay, so that's the whole idea. It's already 3D, very nice, and it just works with P5.js. There's a lot of boilerplate code if you want to do that in OpenGL. So that's also why we use P5.js. Very nice for that. Okay, and the frame of reference 0, 0, 0 is actually make the box really small, like 8. Then the box is around the center, so the center is in the middle of the screen. That's the whole idea. P5.js in 3D. Yeah, that's the fun part about it. Yeah, and we have an error here, and we don't need this. And back to the working version of it. Well. Coordinate spaces are traveled through by everything we want to display, which would be mostly vertices, edges, and polygons, or actually faces of polygons. And we have the model space, and for instance, the box would be a model because it's one thing that appears in the world. And to model the box, we have a relative 0, 0, 0 for the box where we can model it upon. Now I would really like to open Blender. I will do it at the end so that we might avoid a crash in the center of the whole thing. Models have their own space, and each model brings their own space. And in world space, all the models are scaled, rotated, and positioned. So if we have 2 boxes, they have the same origin in the model space, but we move them around so that the boxes stack on each other or lie beside each other. And then, of course, this is just the world as it exists, but we need to look into the world. And to look into the world, we transform it into the view space. So it defines the eye of the observer, it defines the camera or the two cameras if it's a stereoscopic view. Okay, two cameras, stereoscopic view. Two displays, stereoscopic display. I'm just dropping it often that I don't have the same experience asking people about in an exam if a MetaQuest 3 is a stereoscopic device. Then they say no, that would be very bad. Indeed. Projection space then is the view space flattened to a projection. And there are many ways, and there are two main ways of projection, sorry. Projection and orthographic view. Wait, I got slides at the back, so I don't need to remember right now, but we'll come to that. Okay, model space. Models consist of triangles or other primitive, which are defined by the points that we already mentioned with the triangles. And all points are given from the origin. In this case, the model origin, if we're in model space. And of course, without moving them, everything would be gathered around the world space origin too. So we have to move it. Yeah, there is this visualization of axis so that we can actually see what it's doing. Wireframe box with axis. I like it. This one and put in orbit control. Nicer. And we look along, wait, what is it? Red. We look along C, yes. So we don't see the red axis, and we rotate the model and the model space so that the model actually is still having the axis that you can see, but we move the model and the axis with it. So that's the fun part about it. So that shows a little bit when we put in axis into a model space and then transform it to the world space, what actually happens. Okay, so E looks in a different direction than world C. So yeah, box draws a box around 0, 0, 0. No fill just shows the wireframe. We've been there already. Don't forget the WEBGL keyword up there, otherwise it will not work. And of course, you can check it on GitHub. And there are all the JS files, and I think most of the index HTML files too, if needed. Yeah. Box and model space. So that is the old version of rotating. So you can rotate with the mouse, rotate Y, rotate C, but just put in orbit control. I'll just edit this one in here. Insert shape, all out. Use orbit control. And this one should, of course, be better font for that. And so, sorry, live editing. Use orbit control. Much better. Much safer option. Okay, next would be loading a model in P5.js. Of course, you don't need to make everything happen with boxes and ellipses and your own painted paths. So what you can do is you can load a model into your P5.js thingy, and I have it saved somewhere here. Back. 03, transform, translate, model load. Here we are. And I obviously changed and saved the source code, which is not a good idea. Oh, the model is still here. I think that's awesome. So I can just copy the source code over. Put it in here. Yeah, and we have a model, a torus, which is rotating around something. Okay, so how can you do that in P5.js in the web editor? You have to upload the model, upload file, then it's in there, Torus object, and then there's also rubberduck.stl, and then you can just load it with load model and then display it with model T. Let's see if the STL model works too. Well, that's the problem with the wireless mice. If you do not look where you're grabbing them, they just go away. Okay, let's see if... Oh yes, it's a very big rubber duck. But it loaded the rubber duck too, so that's nice. And yeah, we have to actually scale it a little bit down. Oh, we already scaled it up. Oh, here's the rubber duck, okay. But of course, with a wireframe model, it doesn't look too cool. But basically, you know what I mean. You can load any model. If you're searching for models, again, candy.nl brings you a lot of different 3D models, which are free to use. Or, of course, you can take a look at printables, Thingiverse, all those makerspaces where people post their stuff they designed to be printed. Yeah, like this one. Cool. It's RetroPie. I'm just searching for the for the right monitor to actually glue it to, and then I have a retro station. So it's working, but the display device, I don't want to throw money at Amazon again. I'm trying to find a used one here at the university. And then I can run C64 games on it, which is a very important deed. Yeah. Typically, you instance a model multiple times and then just move it there. So if you think of the old racing games, there is always the same tree standing beside the road. It's just rotated and scaled and a little bit thinner or a little bit bigger. So typically for a forest, you need only a few tree models, and then just change them a little bit in scale, rotation, and of course translate them to any other place. And I'm already giving away the 3 basic operations by already naming them all the time. But one more thing. Now we are down to the 3x3 to 4x4 matrices. So what you often do in computer graphics is using homogeneous coordinates. And homogeneous coordinates are made out of x, y, z, and w. And w is either 0 or 1. If it's 0, it's a vector. If 1, it's a point. You know the difference? A point can be basically something that creates 1/3 of a triangle, or a point can give the place of a plane in space, while a vector, for instance, can be the normal of a plane. So you need a point and a vector to define a plane, or something like that. It can give you the normal of a triangle, and then you can use that for shading. We'll come to that. But it's important to distinguish between vector and point. And also with the homogeneous coordinates, we can actually use the same transformation matrices for translating points and translating vectors, because vectors, of course, cannot be translated because they have no point. So you can only translate a position in space, and vectors have no position. But with the homogeneous coordinates, this is actually very elegant. So adding a vector to a point results in a point. That would be this example up here. You have 1, 0 here and 1, 1 here, and then adding them is 1, it's a point. Adding 2 vectors, of course, comes up with a 0 here, so it's a vector. And if you remove a point from another one, you actually get a vector, which is also what we want. If we want to have the vector from A to B, we remove A from B, or subtract A from B, then we get the vector, and it's already done with the 0 here. Adding a vector to a vector, I already said. Adding a point to a point, no way. Then W is neither 0 nor 1, it's 2, and that actually doesn't work. There is, in projection space, there is the opportunity to use W for another thing, and then it's not 0 and not 1 anymore, but it's only in projection space. For that, all the other three transformations, all the other transformations in the three spaces before that, which is model, world, and view space, W is always 0 or 1. At least to the best of my knowledge, and the book I read for that. Okay, the transformation matrices look like that. You have 4 by 4 things, and for a column matrix system, it's not the picture we have, but now we have a row matrix system, and then we transform points like that, basically. Yeah, and long talk, short effect, that would be a translation matrix. So you have a matrix T where you move a point or a vector by x, y, and z, and that's where you put the coordinates that you have to move. And that actually works pretty well because I do not. It works actually pretty well because, and let's see if I can use the pen for that, because if we have this, let's take a column matrix vector, x, y, z, w, and what we then get is a t x times 1 plus, and if w is 0 plus 0, if w is 1 plus tx, and that's actually how we move the vector, or not move the vector, because the vector is a w of 0, and that's actually pretty nice. So you can just compute what comes out of that, and you'll see that you'll end up with tx plus x, ty plus y, and tz plus c. If w is 1, if w is 0, the vector stays unchanged. That's the cool part. Okay, so translation in P5.js. Let's see if we find the source code for that. Here, 3, sketch. That's the one. No, it's just my internet, which obviously still works. Bad gateway. What can I do? Please try again in a few minutes. Thank you very much. Very nice. So Cloudflare is, I always think Cloudflare is a terrorist organization because it makes it harder for me to actually get into the internet. Faisal said it's linear algebra. Yes, that's exactly the point. Yeah, if you know your linear algebra, then computer graphics is just it's applied linear algebra. Awesome. Yeah, as it's an interdisciplinary lecture, I try to start from the beginning because not everybody had the extensive linear algebra training that some people have or had. Okay, so here is the matrix. We have a box of 20 and and a fixed box, and we attach the box to the mouse pointer by having a translation mouse x minus 320, mouse y minus 240, and not moving it in x in y. We can actually put mouse y in here, then it comes out a little bit more if we move it down. Yeah, but you get the basic idea. So that's the translation matrix, and we can use variables in there, and then we have real-time 3D graphics. Pretty awesome. Okay, then what else do we have? We have scale. Scale does work with the same style of matrix, but you put in, instead of the 1, 1, 1, 1, you put in Sx, Sy, Sc, and 1. And then it would scale on the x-axis and the y-axis and on the c-axis. And of course, that is also the case for vectors. So here we have a matrix. And we can scale stuff up, like for instance the box. Always the box. From matrix scaling, that's good. Let's see what Cloudflare lets us do or not. Error. Hello host, error. It does not like me too much. Obviously, hitting reload does not help. Yeah, here we are. So we scale the box a little bit. I'll remove this one again and put in orbit control. And then we can... Oh, that's nice. We have to put orbit control on top of it. And that was already giving away the whole problem with the translations. So it is not like object-oriented programming. It's very sequential, the whole thing. Yeah. And of course we can say, what is it, 0.2 and 1.2. That's more like flat. We can say it's it has a square base, and so on and so on. So we can change the scale in any direction and then create different stuff. Okay. And of course we need rotation, and rotation is based on the Euler rotation. So yeah, it's quite complicated. You don't need to know them by heart, but that's how they look basically. And you can do that on your own. I'll just copy this one and just hope that so we can basically rotate it based on mouse X, which is a very complicated way of, instead of using orbit control, just making a point here. And rotate actually uses the same matrix, so we can remove this one and nothing else happens. So this is just a convenience method to this one. So nobody expects you to write your matrices yourself. You can use translate, rotate, and scale. Those three commands actually do most of the trick here. And I would have really liked to have this code inside here, but yeah, anyway. What you do is you combine the whole thing. So you combine the matrix multiplication. And the problem is that the order is very, very important. Wait, I have to, on the other side, on my GitHub account, see if I find the introduction to computer games course. Oh no, that's the other one. One-time lecture, one-time course. Because then I can just copy it over. And so I'm still moving, great. Double check. So life does not get boring with NVIDIA graphics cards. So the order is important. You do first the scale, then the rotation, then the translation, because if you do it the other way around, it is a very different outcome. And here we have example of that. And that's actually the fun part. Let's do that. So this one, up and down, which is y, rotates, rotates around the x-axis from the model, and left and right rotates around the point after translation. Okay, so if we first rotate and then translate, then it rotates around the mouse, around the model origin, otherwise around the world origin. So I'll just move this one up here. And you'll see that both of the rotations are now around the whole thing. Why? I just said you rotate first and then translate. Bad, Matthias, put it the wrong way. No, that's not the case. Actually, P5JS builds a stack. So what you put first on the stack will be done last. Okay, so what we need to do is put it in reverse order. And then it would rotate around the center point and later translate. So we can translate it, whatever, 200. Oh, I think we cannot really see where this translated to. Here with, yeah, then we can actually, oh no, that's C. Why would I translate it on C? I want to translate it somewhere else, like here. Yeah, but it still rotates around the center point. That is the whole idea of the certain Warlock script, as P5JS named it here. Awesome. Okay, so that's basically the difference, and yeah, also the scaling affects the rotation. So rotation should be very controlled. That's the whole thing. Also, I mean, scaling and translation does work differently. So if I scale it up by, say, 10. Yeah, now it's gone, of course. Goodbye. My model is gone. Because I need to... Oh no, we don't see it because it's too big, sorry. Okay, so now it scales after translation, and that should come to a different effect than doing it the right way. Yeah, because the scale is different. Okay, it's in C, it's moved back, but then it scales everything from the origin to the point 2 times, which is farther away for most of the vectors if we already move it for 200 pixels or meters or whatever we're counting to the back. So that's the whole idea. So switching them around leads to a different outcome, bigger box. Okay, so there is the nice example that I waited for. Okay, now we have this example we saw before. We have a box or a lot of boxes. So I don't know how many boxes. It's 50, 90, and so on. So it's a lot of boxes. And the difference, we push and pop the different transformations. So remember, push and pop, look them up, because you will need a push and pop for your exercise. That really, really helps. And what I had in mind is moving this one here, and we got different rotation because translation is first now. That is the whole idea. For different axes. Okay, so it's different. Okay, so that is the learning here. I don't want to talk too much about it, not because I don't want you to understand it. I want to have you worry about finding it out yourselves a little bit. because we have an exercise on that. So if you're already looking at the slides, which is definitely done by Anonymous Dumbo Octopus, then you already have an idea what I want from you. Okay, the view camera space is the actual eye of the observer. So where does the person or the camera stand that looks into this whole 3D thingy? You can move around in a static scene, so different things are seen on screen, and that's the whole idea. So what you have, or what you need, is you have the look at matrix, which is the position of the camera, which is already great, but in addition to the position of the camera, let's say the USB stick is a camera, you have to look somewhere and also rotate the camera. Let's see how that looks. So L is the left axis, Y is the up axis, F is the forward axis of the camera, and T is the position of the camera, the translation, for a row major left-handed system. That's the definition of the look at matrix. And you can create the look at matrix yourself by using the I, which is the position of the camera, and the target, the point the camera is looking at, and the up vector. So I'm standing here, looking here, but what I still need to know is the up vector, which is defines if the picture is rolled, called rolling. So there's a hugely complex vector to do that all yourself. In P5.js. Fortunately, you don't have to. But what you can do is you can just move the camera. That's the fun part about it. Let's take the source code from here and go to here. Run it. And what we have is we can move the camera. So in this case, not the box is moved, but only the camera. Okay. And what we can also do, we can move the camera with the scroll wheel back and forth. And again, in real time. That's the nice part. And moving the camera is already a first-person walking simulator through your world. I mean, many things come into question then, like how do people actually walk? How high do the eyes have to be? What is the degrees of freedom? Can you kneel down, jump, or something like that? But basically, this is all the ingredients you need for a simple first-person view game. Okay, so projection space is then not necessarily in 3D, because it typically flattens everything to 2D. So that's what we are displaying here in the stream. View space is in 3D, but through the eyes of the observer, but the projection space flattens it to 2D. And there are two different projections, as I already said. One would be the orthographic projection, and the other one would be the perspective projection. So perspective projection is the one where all the lines end at 1 or 2 points in the far distance. So everything that is far behind in the picture is getting smaller. Like you can see the whole mountain, although it's much bigger than the tree you see in front and only part of it. That's because in projection space, things get smaller if they go to the back of the image. And orthographic projection is more like Diablo, where everything stays the same, so parallel lines stay parallel. Let's take a look at that. So that is source code for switching between orthographic and perspective projection. So we have the mouse thingy again, so we can move the mouse. With the mouse we can move the camera, and as you can see, all the lines that should be parallel are kind of distorted. Okay, so now I have the mouse. No, I cannot point with the mouse here because if I move the mouse, whatever. So the cube is distorted, but it feels natural because we have this perspective view anyway. And that is the orthographic view, which does not look natural at all, but it's more like Diablo, and their parallel lines stay parallel, which doesn't look like it, but it does actually. So you can take out a ruler or something like that and check it. Okay, and that would be the perspective view again. Orthographic perspective. So why would we need the orthographic view? As I said, there are games like isometric games that actually need it. You have a side scroller, for instance, and you do it in 3D, then you typically use an orthographic camera, and so on and so on. So there are several use cases actually which are not extremely intuitive in the first moment, but there are some. Okay, and that's an explanation of that. You have a far plane, you have a near plane, and in between is everything that you can see in your projection. And for orthographic projection, it's just projected in parallel lines to the near plane, which then basically is your screen. So that's the whole idea. Everything stays the same in types of size, and Diablo or The Sims are games that actually use that. And here you have not a box, but the view frustrum, which is a pyramid with the pointy end cut off. And things that are nearer, like the green one here, are bigger. And things that are farther away, like the violet one here, are smaller. That's the whole idea. You again have a near plane and a far plane. But what you also have is the angle of this frustrum. It's the field of view. That sometimes you can actually blow that one up for computer games and gives you a very weird feeling if you put it up too high. Okay, the projection matrices, it's just a matrix multiplication with every single point you have in view space. And what you do is something like that, far and near, and that's quite easy. So we can now test the orthographic projection with a lot of boxes, because you always have a lot of boxes. So we have these many boxes, and they're actually orthographic. No, not orthographic. That's the orthographic projection. Sorry. And I can change the near plane by moving the mouse up and down. So things are just cut off. And if you look closely here, then you see that only parts of it are cut off because it cuts off on a per point basis here. It does not cull the whole object, but only the points. And in perspective projection would look like that. So that's basically the difference. It's huge if you put it up that way. And the projection matrix, we already saw the many boxes demo. The field of view is important. It gives us how much we can see, and in terms of view angle. And yeah, the scale in X and Y are created based on the field of view and the height and the width of the screen, actually. What is interesting here is that the W component is no longer 1. After this perspective projection matrix, the W component is some number, and what you actually do is each of the vectors or points you vector wouldn't change, sorry. Each of the points you run through the projection matrix is then divided by the W component, so that the W component becomes 1 again. And this adds the sense of depth, the perceived depth, because then it makes the things that are farther away smaller. That's the moving for me. Or you're trying it out, most likely. Okay, so yeah, we can then change the field of view with the mouse wheel. Let's put it in here, and the steps are huge. Make it smaller. Sorry. And smaller. And it looks like we're zooming out, but what actually, thank you very much. Video is stuck only for me. It's moving for me. Ah, okay, I didn't see the, yeah, I didn't see the question, sorry. Yeah, I'm double checking. Always when I look like that, I see if I'm moving. I have to be fast. So in this case, it looks a little bit like zooming in, but it actually isn't. What it is it's narrowing the view space, and then of course you have more pixels to display the same information. It looks like zooming in. Sometimes this is used as zoom in, but it also distorts the view. That's the downside of the whole. Okay, so that's the field of view, and now for the exercise. And I like to show you what Tom submitted in his time, which was perfect. You should create a scene of 2 boxes in B5JS. So that's easy. That's 2 times the box command. You should let them rotate automatically and slowly, and both around their own y-axis and them around the center point between them. It should look a little bit like that. And that's quite hard, okay? Sometimes people just manage in 5 seconds. Sometimes it's just, is it okay if they rotate the same way? Yeah. If the y-axis is rotating the same way for both, that's also okay. And so it should look like something like that. And they don't have to rotate the other way around, not necessarily. Also, the same way would work. It's a little bit easier, actually. But yeah, that's not the hard part of it. Okay, so that's it from my side. I hope we can create a video out of those 2 snippets I recorded today. And well, are there any questions?